this AVL is representing the name of the scientists. For the honorary, we are using the scientist names to represent this tree, AVL tree. AVL tree can be defined as height balanced binary search tree. So already we covered what is binary search tree and what is height also, right? So this is height balanced binary search tree in which each node is associated with balance factor. Then what is balance factor? How to calculate that? So balance factor is calculated by subtracting the height of the right subtree from the height of the left subtree. I will show you the formula in the next slide. A tree is said to be balanced tree if the balance factor of each node, let me repeat, this is very important point. A tree is said to be balanced tree if the factor of each and every node in the tree, the values of the balance factor between -1 to 1. The balance factor of the every node should be in the range of -1 to 1 only. If the balance factor value is other than these values, that is unbalanced tree. That tree will be unbalanced tree. We need to balance that. See the formula for the balance factor. Balance factor K is nothing but a particular node. Balance factor equals to height of left subtree of that particular node minus height of right subtree of that particular node. If balance factor of any node is 1, it means that the left subtree is one level higher than the right subtree. As I said, generally the balance factor value should be 1, 0, -1. These values are valid. Okay. Then only we can say that that tree is a balanced subtree. So what is the meaning if we have the balance factor value is 1? The meaning is left subtree is one level higher than the right subtree of that particular node. So that is the meaning of balance factor 1. Second case, if the balance factor of any node is 0, it means that left subtree of that particular node and right subtree contain equal heights. Left subtree and right subtree of the particular node contain equal heights, then the balance factor of that particular node will be 0. Third case, if balance factor of any node is -1, the meaning is that the left subtree is one level lower. The left subtree level is one level lower than the right subtree. Then we get the balance factor -1. Okay. Already we covered height, but let me tell you once again because the height is very important. We are using the word frequently. What is height of a node? The height of a node can be defined as the length of the longest path. The length of the longest path from that particular node to the leaf node of the particular tree. That is called height. See this example. This is AVL tree and this is height balanced tree. How can we say this is height balanced tree? See this. This is balance factor value. This particular node 100, balance factor is 1. 50 node balance factor is -1. 150 node balance factor is 0 and 175 balance factor is 0 at 125, 0 at 75, 0 and 85, 65, 25. All these nodes balance factor is 0. As we covered just now, if we have the balance factor minus 1, 0, 1. Then we can say that that tree is height balanced tree and AVL is also height balanced tree. Right? Now, let me tell you how we calculate this balance factor. See the height of this particular node. What is the height? Longest path from this node to its leaf node. What is it leaf node? 25. Root node and the leaf node is 25. Longest path from its leaf is 2 edges. Okay. How many edges we have? One edge, second edge, two edges. So the height of this node is 2 if we follow this one. But as per the definition, longest path, na? Next. Suppose if I follow this direction, right side, 1, 2, two edges and we reach the leaf node. If we follow this method, 1, 2, this is also two edges. It has two edges. But now let me show you one more path. One edge from root 100 to leaf node. One edge, second edge, and third edge. So height is the longest path from this particular node to leaf node. So we have the path or longest path or height of 100 is 3. Left side. Right side 2. 3 minus 2 equals to 1. This is the balance factor. Okay. Right hand side height minus left subtree height. That is balance factor. For example, come to the 50. Left subtree only one node, one edge. So how many edges we have from this 50 to its leaf node? Leaf node is 25. A node which doesn't have any child nodes is called leaf node. We covered that already. So 25 is a leaf node. So how many edges we have from 50? Only one edge. So 1. Left subtree height is 1. Right subtree. See the right subtree? So this part is right subtree, right? So what is the height of the right subtree? Longest path, 1, 2. Two edges. So height of the right subtree is 2. Now see, balance factor 1 minus 2 equals to minus 1. The balance factor of 50 is minus 1. Okay. So in the same way, we need to calculate the balance factor of all the nodes. In the case of 150, 1, 1, 0. Like that. What are the operations can we perform on AVL tree? Due to the fact that AVL tree is also a binary search tree, we can perform all the operations. What can we perform on the binary search tree? Okay, what are the operations we can perform on binary search tree? We can perform all those operations on the AVL tree also because AVL tree is also a binary search tree. Searching and traversing do not lead to the violation in the property of AVL. So when we perform any searching operation or traversing operation, we covered already what is traversing, right? Visiting all the nodes. So when we implement searching and traversing operations, that will not affect the properties of the AVL trace. Fine. But when we work with the operations like insertion and deletion, those can violate the properties of AVL tree. So when we work with insertion and deletion, we need to balance it again because AVL should be balanced. As we covered the operation insertion and deletion, insertion in the AVL tree is performed in the same way as it is performed in the binary search tree. However, it may lead to the violation in the AVL tree property and therefore the tree may need balancing. So the tree can be balanced by applying some rotations. This is important part. Okay. So here the point you must understand is while performing the insertion operation, the AVL tree might be imbalanced. To make it again balanced tree, we need to use some rotations. In the same way for the deletion operation also. When you implement a deletion operation that might be imbalanced, you need to balance it by using the some rotation operations. Then let me tell you what is why we use AVL tree. What is the importance of AVL tree? AVL tree controls the height of the binary search tree by not letting it to be skewed. This is important point. Okay, so with help of the AVL tree, we are trying to maintaining the balanced. With help of this, there is no chance to creating of these skewed trees, like right skewed or left skewed trees. The time taken for all operations in the binary search tree of height h is order of h. If we assume that the height of a binary search tree is h, then the time complexity or time taken for all operations in AVL is order of h. However, it can be extended to order of n if the binary search tree becomes skewed. The skewed is worst case that takes more time. By limiting this height to log n, AVL tree imposes an upper bound on each operation to be order of log n. Okay, the upper bound for the all. Now, as I covered just now, we need to do some rotations to make a imbalanced tree as balanced tree. What is rotation and what are the different types of the rotations we have? We perform rotation in the AVL tree only in case of if the balance factor is other than the value -1, 0, 1. We covered that already. So the four types of the rotations we have, those are LL rotation, RR rotation, LR rotation, RL rotation. L means left, R means right. LL rotation, left, left. When we use LL rotation, inserted node is in the left subtree of A. If you assume that we have the node A and inserted node is in the left subtree of A. In such cases, that becomes imbalanced tree. To make it as balance, we use LL rotation. If we insert the node in the left subtree of A. Okay. Left subtree means this one. Okay. For example, C. A is left subtree of C. C's left subtree is B na? B's left subtree is A. Now we can say that A is left subtree of C. Right? In the same way, LL rotation is used when we insert a node, a left subtree of A. RR rotation, same thing. Now you can understand it easily if you understand LL. If we inserted the node in the right subtree of A. And LR rotation, when you insert a node in the right subtree of left subtree of A. Right subtree of left subtree of A. Then we can go for the LR rotation. RL rotation. If you insert the node in left subtree of right subtree of A, then we can go for the RL rotation to make that tree as balanced tree. See, with help of the diagrams, you can easily understand it. RR rotation, right rotation. When BST becomes unbalanced due to a node is inserted into the right subtree of A. This is A. B is right subtree of A and C is inserted at right subtree of B. So now we are inserting C as right subtree of A. So in such cases, the balance factor will be 2 for root node A. So this is other than 1 minus 1, 0. This becomes unbalanced tree. So we need to balance that. So when we insert a new node as right subtree of a node, we need to implement RR rotation. This is the major important point you must remember. Then see, this is then we perform RR rotation. RR rotation is anti-clockwise rotation, which is applied on the edge below a node having the balance factor -2. So now the height of the root node is 2. What is the balance factor? Left subtree height. Here we don't have any left subtree. So the height of the left subtree becomes 0. 0 minus 2. It becomes -2. The balance factor of A is -2. So whenever we have a height of any node other than -1, 0, 1 that becomes imbalanced, we need to make it as a balanced tree. So for the right notation, that is anti-clockwise rotation. See, that should be applied on the edge below a node having balance factor 2. Which node balance factor is 2? A. So below that node, what is the edge we have? We need to apply on that edge. So that should be rotated to anti-clockwise. That is R notation, RR notation. So A must be comes here and B, C. Now the height of B, A, C is 0. Now it is balanced. So in the above example, node A has balance factor -2 because a node C is inserted in the right subtree of a right subtree. That's why we perform RR rotation. LL rotation, when binary search tree becomes unbalanced due to a node is inserted into left subtree of C. Then we need to perform LL rotation. LL rotation is a clockwise rotation. LL rotation is clockwise rotation and that should be applied on the edge. That should be applied on the edge. This is important point. Below a node having the balance factor 2. So here the balance factor of C is 2. 2 minus 0 because left subtree height is 2. Right subtree, there is no right subtree. That's why height is 0. So below the edge of balance factor 2 is B. So that must be rotated to the left hand side clockwise, LL rotation. So if we rotate to the left side, the C becomes right subtree of B. This is about LL rotation. Next, LR rotation. Double rotations are a bit tougher because we need to use here double rotation, right, left, LR, left, right. Okay. So the formula or steps we used while working with LR rotation is first we need to implement RR rotation. Already we know that how to implement RR rotation plus RR rotation plus LL rotation. That is what? LR rotation. First, RR rotation is performed on the subtree and then LL rotation is performed on full tree. By full tree, we mean the first node from the path of inserted node whose balance factor is other than -1, 0, 1. See, suppose we inserted a node B. A node B has been inserted into the right subtree of A, the left subtree of C. A is left subtree of C, B is the right subtree of A. Now, it becomes unbalanced because the node C has balance factor 2. Now we need to balance it. This case is LR rotation where inserted a node is the right subtree of left subtree. As LR rotation equals to RR plus LL rotation, hence RR anti-clockwise on subtree rooted at A is performed list. So by doing RR rotation, node A has become the left subtree of the B. After performing RR operation, node C is still unbalanced because still the balance factor is 2 only. Now we perform LL clockwise rotation on full tree, that is on node C. C has now become the right subtree of node B and A is the left subtree of the node B. Observe here. So this is the final one. RL rotation. As already discussed that double rotation are a bit tougher than single rotation, which is already explained in the LR rotation. Okay. Now RL rotation, first we need to perform LL rotation plus RR rotation. That is, first we need to perform LL rotation and the subtree, then perform RR rotation on the full tree. See the example, a node B. A node B has been inserted into the left subtree of C of C, the right subtree of A, because of which A has become the unbalanced tree because the balance factor of A is 2. For this, we use RL rotation. Inserted node is in the left subtree of the right subtree of A. As RL rotation equals to, we covered LL rotation plus RR rotation. Hence LL, that is clockwise and subtree rotated as C is performed first. So by doing RR rotation, node C has become first right subtree of B. After performing LL rotation, node A is still unbalanced. Okay, still unbalanced because it has the subfactor -2 because there is no left subtree. 0 minus height of A, that is 2. 0 minus 2 equals to -2, that is the balance factor. Now we perform the RR rotation, that is anti-clockwise on full tree, and that tree becomes like every node contains 0, 0, 0. The height is 0, so the balance factor becomes 0. So there is no problem with this. Now next topic is searching. So we completed sorting techniques in one of our session already, like bucket sort and radix sort, insertion sort. Okay. And coming to the searching also, we have two algorithms. So many techniques are there, but as per our syllabus, we have two algorithms for the searching. Now, before going to that, first let us try to understand what is searching here. Very simple. Suppose if we lost any object, we are trying to search about that object. Okay, searching for an object to get that. In the same way, searching is a process of finding some particular element. in the given array. If the element is present in the list or in the given array, then the process is called successful searching. If the element is not found in the given list or array, we can say that that is not a successful or unsuccessful search. There are two popular searching techniques available. Those are sequential search. That sequential search is also called linear search. Second category is binary search. So let us start with first one. You can use the word linear search or sequential search. Those two are valid. Linear search is the simplest searching algorithm that searches for an element in a list in a sequential order. This is important part. So the name is sequential search, sequential search or linear search. So we are going to search for a particular element in a sequential order. That's why it is called sequential search or linear search. We must start the ending process for the one end and we need to continue to reach the another end. If the element is found, we can return the information to the user. If not found, uh, uh, we must display that the element is not found, like that. Linear search is mostly used to search an unordered list. This is also very important point. So here linear search or sequential search is used to finding for a element in the unordered list. The list is no need to be in the order list. No need to be in either ascending or descending. You can take any unordered list and implement a linear search algorithm. How linear search works? Very, very simple searching technique it is. For example, we have an array. In that array, we have the elements 2, 4, 0, 1, 9. We have these elements, let us say. Now the k value is 1. K value equals to 1 means key value equals to 1. The meaning of that is I am going to search for 1. So actually, as a developer, you know what are the elements are available in the given array. But as a user, I don't have any clarity about. So we need to search about the 1. Okay. But as a developer, you know what are the elements we have in the array. But as a user, the user doesn't have any idea about what are the elements the array has. So the user is trying to searching for one. The one may or may not be found. The user may not have the idea. The one may or may not be available. So that's why he started searching for one. Then the procedure is first the value for which we are going to search, that value should be stored in a variable. That variable name is k, where k represent key. Okay, we are searching for one. In the step one, we must compare that k value with the first value. What is the first value we have in the given list or array? That is 2. But in the k, we have the value 1. So 1 is not equals to 2. Okay. 1 is not equals to 2. Then go for the next element. Index value must be incremented. Next element, that is second element, is 4. Compare k value with 4. But k value is 1, not equal. Then go for the next cell. Compare with 0. This is also k value is not equals to 0 because k value is 1. Here we have third cell value 0. These two are not equal. Then go for the fourth cell. Compare the key value with this fourth cell value. So that is valid, that is equal. So now we can say that the desired element is found and we can display the message like the element is found at this particular location. For example, if I search for the 3, let us say k equals to 3 because I am searching for 3. This is another case. That 3 must be compared with 2, not equal. 3 compared to 4, not equal. 3 compared to 0, not equal. 3 compared to 1, not equal. 3 compared to 9, not equal. So in this case, we must display the information like the element is not found in the given array. Okay. Before going to the binary search, let me show you the code related to the linear search. So this is the Java implementation of linear search. See, this is main method. First, I created one array. Okay, I created one array. Array name is ARR. The elements we have in the array are 3, 4, 1, 7, 5. 5 elements we have. Okay. Now I am going to searching for 4. As a developer, you know what are the elements we have already in the array. But as a user doesn't have idea about your code. So that's why, whatever the number the user wants to search, we need to store that key value into any variable. So I'm storing that I'm storing that value in a variable called x because I'm searching for the 4 and 4 will be stored in a variable x. Now we have the one method with the name search. Search is a method that has two parameters. One is array, second one is variable. So in the array, we have the values 3, 4, 1, 7, 5. Now in the x, we have the value 4 for what we are going to search. Now this is the function calling statement. It is going to redirected for the that relevant function definition. Let us see, do we have any function in our program with the name search? Yes. So it is going to be redirected to the search method and the array elements are stored in this array. You can use any other name also other than ARR and the searched element will be stored in the variable X. Now I want to search for that particular element in the entire array. Before that, we must know what is the length of the array. Okay. For that, I am using the property length property of the array object that returns length of the array, where length equals to how many numbers that array has. See how many numbers we have in the given array? 5. So array dot length gives 5. So now in the variable n, we have the value 5. Right? Now see the sixth statement. For loop I equals to 0, I less than 5, right? Because n value is 5 now. I less than 5, I plus plus. Now we need to compare the first index value, array of I, because in the first iteration, I value is 0. If array of I means array of 0. So what is the element available at the 0th index? That is 3. Now this value 3 is compared with x. What is the value we have in the x? 4, right? We stored 4 na? And with help of that, we call this method. So we have 4 in the X. So 3 is equals to 4? No. If it is yes, return I. But in this case, this is not true, right? And it's into this part. It goes to the I plus plus. Index will be incremented and index value becomes 1. And the element available at the index 1 is 4. Now array of 1 is 4. 4 equals to x. X value is also 4, right? So 4 equals to 4. This is true. That's why it returns I. I is nothing but index value, that is 1. So we found that the element 4 in the index 1. Now this index I is returned to the calling place. Where we have written calling place here. That index value will be assigned to the variable index. Now, if index equals to -1, system dot out dot println element not present in the array. Okay. But in our case, this is not true because we found that 4 in the index 1. Else, so else will be executed because it becomes false. Because index value is 1, not -1. So that's why this will be displayed system.out.println elements not found in the index. But as per our example, 4 is the key element, 4 is found at index 1. So let us execute that. What type of the output will we get? Let us observe. See, element found at index 1. Which element? 4, right? Suppose if you want to write with more clarity, you can write like this. Array at the index. Okay. Element not present. In the same way, you can write for this also. Let me execute it. Now see, 4 element found at index 1. Or if you want to write element 4 found at index 1. Okay. Now, for example, I want to pass 8. X value is 8. Okay. Save it. Control S. I am using VS Code to execute this code and run it. Index 8. Then next, Next is binary search. So sequential search is searching an element from 0 to n. First, we need to compare the element with first element and second element and third element and so on. We need to compare the particular element with all the index values. So coming to the binary search, we are following some rules. The first rule is the elements must be sorted. The elements must be sorted. Otherwise, we cannot implement a binary search technique. Okay, that is the first rule. Next one is actually why we go for the binary search. So in the linear search, for example, I am searching for 9. So we need to compare all the values. Then at the last, we will get 9 is available. That type of information we will get. Suppose I have 100 elements and I am searching for 9, where 9 is available at the 99th index because that is 100th element. So index is 99. So searching for the element 9 takes lot of time because that is available at the last index. Because we need to search in the sequential order, that takes lot of time if when we have more and more elements in the given array. So this is the drawback of linear search or sequential search. To overcome that, we have one more method called binary search. This binary search follows divide and conquer approach in which the list is divided into two halves, two parts, and the item is compared with the middle element of the list. If the match is found, then the location of the middle element is returned. We search into either of the halls depending upon the result producing through the match. See this example, you will get a clear idea with help of this example regarding binary search. Suppose we have this array 1, 5, 7, 8, 13, 19, 20, 23, 29. Yeah, I'm writing index values of these 0, 1, 2, 3, and so on, 8. Now I am searching for 23, let us say. Okay. I am going to search about 23, whether 23 is available or not in the given array. I am searching. First rule is we need to find out middle value of this given array with the help of the formula starting index value plus ending index value by 2. Beginning and ending. 0 plus 8 by 2, that is 4. So middle index value is 4. This one, fourth index. Now this element must be compared with the searched element. Searched element is 23. The element to be searched is 23 and the middle element is 13. So we know that already all these elements are sorted. In this example, I am assuming that these elements are in the ascending order. Okay. In our example, the elements are sorted in the ascending order. I am searching for 23. So middle element is 13. So we can easily understand that the 23 must be available at the right hand side of the 13 only because all these are sorted already and this is 23 is greater than 13. That's why that must be available at right hand side of the 13. So in this case, we can ignore the left hand side. Okay. So this is important point you must understand here. Now, coming to the right hand side, this part is now our working area, right? So this is end point, no changes. But coming to the starting point or begin point becomes end plus one. Sorry, middle plus one. So in the last step, this is the middle value, na? Mid equals to 4, mid value. So in the next iteration, the starting value or beginning value of the new working area becomes beginning equals to mid plus 1. Okay. In the previous case, mid value is 4. 4 plus 1. What is the mid value? 4. 4 plus 1. 5. Okay. So this is 5. Now, for this working area, we need to find out the middle value once again. Okay. 5 and 8. 8 plus 5 by 2. And after that, depending on the middle value, again we need to search. If the searched element is less than the middle value, we need to search in the left hand side of the middle value. If the to be searched element is greater than the middle element value, we continue the searching operation at the right hand side. Third case, the element must be same as the middle element. We may have three cases. Okay. So like this, we need to continue the binary search technique. Let me repeat in brief again, binary search. First step, rule 1 must be in the sorted order. These are in the ascending order. I am searching for 23. Find the middle value by using the formula beginning and ending by 2, beginning index and ending by 2, that is 4, middle value is 4. And find the element available at fourth index 13. So this is 13, but I am searching for 23. And all are in the ascending order. So 23 must be available at the right hand side. So you can ignore the left hand side. No need to work with left hand side elements. No need to compare with the left hand side elements. So with this, we can save our time. So this is the advantage of binary search. Okay, because we are ignoring the left hand part completely. That's why it takes less time compared to the linear search or sequential search. Now, in the next one, so this is our working area. This is our working area. Finding the middle value. Middle value index is 6 and element available at 6 is 20, but searching for 23. 23 must be right hand side of the 20. So you can ignore left hand side. Okay. Then like that, you can still divide that. 7, 8, we have two values only. Mid value, find the mid value 8 plus 7 by 2. And we will get the index value 7. What is the element we have at the index element 23? And we are searching for also 23. So return the information like the searched element 23 is available at the location 7. So this is the algorithm of binary search. Let me show you the code related to the binary search. If you understand the algorithm, it is very, very easy to understand this code also. And now see, main method and creating the array first. And observe here, this array is already sorted because the rule we know that if you want to work with the binary search, that elements must be in the sorting order. Now the element to be searched is 10. I'm storing the 10 in target because I want to search for the 10 and calling the method binary search. And for that method, we need to pass two arguments, array name and target. So where we have that method binary search, we are receiving the array values. And here also, I'm using the name ARR and the target value is stored in the target variable. Now, as we covered begin, end, middle. So you can take begin, end or left, right or start, stop. You can take any variable name. Left equals to 0, right equals to length minus 1. Okay. So in the case of 10 elements, the index value becomes 9. Length of the array minus 1. Okay. Then if while left greater than or equals to right, always left value. Starting value must be less than or equals to right. Okay, that is common rule. Until that, find the middle index first by using the middle formula, left plus right by 2. Okay, and compare that value with middle value with the target, and you can return mid value when the target value is equal to the middle value. If the middle value is less than the target, that middle value is less value than the target, nothing but target value is greater than, that must be available at the right hand side. So you must ignore left hand side, and left becomes, and the new value of the left becomes mid plus 1. So in the same way, if the target is smaller, ignore the right hand side, that is right half, and right value must be updated using the formula right equals to mid minus 1. Let me execute this. See element found at index 4. Let us see this. What is the element we passed? 10. See 0, 1, 2, 3, 4. Fourth index. So the 10 is available at the fourth index. Like that, we'll get the information as an output. Okay. This is about searching techniques. Okay.